So like I said in the previous video, we are going to use technology to help us go through this process of approximating a solution, finding the tangent line, finding the new x-intercept, and repeating until we get close enough to our solution. Okay, so to do that, we're going to start with a little bit of algebra. All right. The first point that we're going to approximate is the x value of our solution. Okay. And you can be as close or as far from this as you want. I would recommend, just pick the closest integer. Okay. And that's usually going to be close enough. So we start by graphing our function and then visually approximating what that x-intercept is, and we're going to call that x1 since we're going to be repeating this several times. So x sub 1 will be our first x-intercept, x sub 2 will be the second, x sub 3, etc. until we get close enough. Okay, then we're going to write the equation of the tangent line at that point. Well, actually, we're not going to write out the whole equation. We are going to use the equation of the tangent line. And then we're going to find the x-intercept of that tangent line, which would be the new x value. So that'd be x sub 2. And then we repeat those two steps over and over. Okay. I'm going to start with point slope form of a line. Okay. So y minus y1 equals m times x minus x1. And then I'm going to replace the, that one is not great here. Y sub 1, okay. Then I'm going to replace the y with y sub 1 with f of x sub 1, just to use function notation. I'm also going to replace the slope with the slope of the tangent line, meaning the derivative at that point. So that's going to be f prime of x sub 1. Okay, so we've got y minus f of x1 is equal to f prime of x sub 1 times x minus x1, okay? And then, so this is the equation of the tangent line written in point slope form, where this value is actually f of x sub 2, okay? But it's gonna disappear anyway. So, because what we want is the x-intercept, so we're going to set y equal to 0. So I'm going to replace this with a 0, and then we have negative, I mean, you could write the 0 here if you want, but negative f of x sub 1 equals f prime of x sub 1 times x minus x sub 1. I know that's a lot of x's, but we're going to clean it up a little bit. And then in this equation, we want to solve for x sub 2. We want to know what is the second point, okay? Oh, actually, apologize. I should have an x sub 2 there because our x-intercept is actually the point x sub 2 comma 0. So we should have a 2 on there already when we replace the y with a 0. Okay, so now we want to isolate this. So I'm going to do two algebra steps. I'm going to first divide by f prime of x sub 1 to get this piece by itself, and then add x1 to both sides. So we end up with x2 is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. If you want to do that in two steps, that's fine, but I just went ahead and did both algebra pieces at once. Okay, so what I have here is I now have an equation that is the second x-intercept written in terms of the first. Okay, so first x-intercept, this is our estimate, remember, minus the y value at that point divided by the derivative at that point. Okay, and this gets us to our second estimation, which ideally, if we chose a decent first estimate, is going to be closer to the x-intercept. All right, now we will repeat this process. So then x sub 3, we could write as this x-coordinate, so x sub 2 minus f of x sub 2 over f prime of x sub 2, and then x sub 4 is equal to x sub 3 minus f of x sub 3 over f prime of x sub 3. I think you get the picture. And we continue that process until we have gotten close enough. Now, close enough is going to be determined by the problem. So it might say to this many decimal places. If that's the case, you continue repeating this process until it stops changing at that decimal. Okay, and so you'll see here an example when we do this first one. So this right here is just the generic form of how we would write that, okay? So if we have a function and now this only applies if the function is differentiable, but that you won't be asked to use this on a function that's not differentiable because it doesn't apply, all right? And then x sub 1 is our initial approximation of r. When it says r where f of r equals 0, that means that r is the solution, and that's what we're trying to solve for, okay? And then E represents the error. That means how far off can we be. So it'll be given to you as like approximate this solution to 5 decimal places or 7 decimals or something like that, and that's what that means by error. So we repeat this process until the difference between the actual solution and the difference between the n+1th and the nth x-intercept, or in other words, our current x-intercept and the previous x-intercept is smaller than that amount of difference, because that means we're close enough, okay? All right, so, and then here's your general formula for the n+1th x-intercept in terms of the nth, all right? So if I said that I wanted you to write an expression using Newton's method that would find the 6th x-intercept, you would say x sub 6 equals x sub 5, because that's the n+1, minus f of x sub 5 over f prime of x sub 5. Okay, so for this first example, we've got f of x equals x cubed minus 3x minus 5. We are trying to approximate the real root of this, all right, or the x-intercept, and we want to go to 7 decimal places. So I have this graphed. Okay, so I've got this function here already entered. Go ahead and graph it. And as you can see, our x-intercept, or our solution, appears to be just a little bit bigger than 2. Okay, now, if we wanted to, we could start at x sub 2. I'm going to actually start, or we could start at like x sub 2.5 or 2.3 or something like that. I'm just going to start at 2 for just to start with an integer, okay? So when I write this out, as far as showing work, this is what I need to show. So I need to show a chart that indicates which step I'm on, okay? So like my first x-intercept, or my estimate, and then over here what that value is. So I'm starting at x equals 2, and then this is just going to be, you know, etc. However far we need to go until we stop changing at the 7th decimal. Okay, so we need to evaluate this on a calculator, or more generally, we need to evaluate this. So this is how we are going to enter it on a calculator. We are going to obviously put our function into y1, okay, and you see I've already done that. So we've got the function in y1. Okay, and then we're going to visually approximate the x-intercept, okay? Now, f of x sub n, that is the y value at our x-intercept. Okay, so let me label this. So I'm going to have to keep flipping back and forth between using the actual mouse and the pen here. So this right here is y1, okay? And then we know how to find a derivative on a calculator. Again, this is something Newton would do by hand, but we're using our technology that we have. So this right here is going to be y sub 2, okay? Or y2 in our graphing calculator, all right? And actually, we're going to go one step further, and we're going to let y sub 3, we're going to make this equal to y1 over y2, okay? So y3 is actually going to be this fraction right here, so that when we want to find the new x-intercept, all we have to do is the previous x value minus y3 of that x value, okay? So on the calculator, we want y sub 2 to be the derivative of the first function. Now, is that function x cubed minus 3x minus 5 something I can take the derivative of in my head pretty quickly? It is. However, what I am going to show you now is how to set up your calculator so that you do not have to repeat any derivative by hand, and it's already ready for you no matter what function you plug in for y1. Okay, so to do this, we're going to go to our derivative, which is math 8, okay, and it's the derivative with respect to x. and then of function y1. Again, don't retype it. We want to do this in terms of y1. So I'm going to do alpha trace, okay, and then y1, and then over at the point where x is equal to x, okay. 83 people, just a refresher, you are going to do, yours will say n-deriv, and so you're going to put the function y1, which you need to go to variables, y variables, function y1, okay. I think I have a previous video in Unit 2 about finding derivatives on a calculator that involves an 83, so if you need to go back and look at that, do that. So y1 comma x, all right, at the point where x equals x. And then for y3, we're going to put y1 divided by y2. So alpha trace to retrieve y1 divided by alpha trace, and then arrow down to y2. Again, you can also get to that from variables, y variables function, okay? All right, so now I do need to approximate my x-coordinate from the graph, and it will take your calculator a long time if you try and graph like this, because it will have to recalculate the derivative of the first function at every value of x. So I strongly recommend that you turn functions 2 and 3 off. Don't delete them, but just hover over the equal sign and hit enter so that it's no longer highlighted, and then the calculator won't try and graph it. Okay, so when we go back to our graph, and remember we already decided we were going to start at x equals 2. Okay, so we get our approximation from there, and then we go to our home screen. Okay, and so we are going to evaluate x, which we're starting at 2, minus y3 of that value. Now, I'm not even going to put 2 minus y3 of something. I'm going to simplify it even one step further so that my button pushing is going to be minimized. What I'm going to do is my first x coordinate I'm going to store as x. So whatever I want my initial estimate to be, so again I'm picking 2, I'm going to hit the stow button here, this means store, and then the x button, okay? And so I'm going to do x minus, and then retrieve y3, so again alpha trace, go down to y3. Now you can put of x right here. Actually, if you don't put the parentheses of x here, it will automatically plug your x coordinate in, so this part is actually extra. Don't hit enter yet though, because again we're trying to minimize our button pushing. So then hit store x. What this is going to do is it's going to take the value we have at stored as x, which we're starting at 2, minus, and then it's going to evaluate y3 at that point. And remember, y3 is y1 divided by y2, or the function divided by the derivative of the function. So again, this will be at x equals 2. And then we're going to store that as the new x value. In other words, we're going to get our x sub 2, okay? And we're not just going to find x sub 2, we are going to store x sub 2 as the new x value. Okay, and we hit enter. And I know that seems like a lot, but I'll show you why we want to do all of that first. So this tells me that my next x-intercept, okay, getting closer to the solution, is 2.333333296. And you do need to go to several decimal places. So 2.333333296. 1, 2, 3, 4, 5, 6. Okay, you need to go at least to 8 decimal places because we want accuracy to 7. Okay, now here is the nice thing about what we just did. Okay, and this works 83 or 84. All I need to do now is just hit enter again, and the calculator is going to repeat that process. Let's see here. Okay, there's our x sub 3. Hit enter again. There's our x sub 4. And then I do need to write these down, but we're just going to continue to hit enter until it stops changing after the 7th decimal place. Okay, so x sub 3 is, let's see, 2.280, and then 5 5s, and then a 7. Okay, so 2.280, 5 5 5 5 5 7. Okay, and then 2.2790 to 0068, 2.2790 to 0068. This would be easier if I didn't keep covering the screen up, but that's all right. And then enter again. Oops. Enter again, enter again. Just move this over. And then I'll be able to see it. Okay. And if you notice, it has stopped changing, okay? This value has stopped changing. That means any change that is happening after this decimal place, meaning I have to be accurate to at least this many decimal places. So let me go ahead and finish that. So that's 2.279018786, and then 2.279018786. Okay, so once I get that there's no change, okay, I know that I have accuracy that far, and we wanted 7 decimal places, so that's going to be 2. So actually, my solution is that x is approximately 2.27901.8, and then this is the 7th decimal place that we're rounding to, so 8. Okay? All right, so what I would like you to do is to pause it and try this next example, okay? And then just a hint, remember that we should be in radians, okay? And then resume it, and I'll put the solution up so you can see if your chart looks the same as mine. Now, if you have a different initial x estimate value, your solution, your chart is going to look different than mine, okay? So you can start wherever you want, but you should end up with the same solution. Okay, I started mine at 2.5. Again, if you started somewhere differently, you might have a different number of steps and different values here, but you still should close in on the same value, which is a solution of approximately 2.5541960.